Welcome to Keystone Tutoring. Today we'll be talking about how to find the local maximum and minimum of functions. This is our continuation in our series of differentiation. And just to provide an overview, today we'll be talking about the local maximin versus the global maximin, steps to finding the local maximin, and one example which we will go through in thorough detail to provide all necessary information. So the local max and min versus global maximin. So the local maximin is the highest and lowest points respectively. So highest for max, lowest for min, within a specific area of the function, so within a specific range. And the global maximin is just the highest and lowest points respectively throughout the entire function. So looking at the graph below, this black line here represents a function. And let's say we wanted to find the local maximin between these two red periods. So between, let's just say that's x equals 2 and that's x equal to 6. The local min between these two, as we can see here, is the lowest point, the lowest value, and the local max is the highest value within this range. But if we were to expand it to the whole line, and this would continue on forever because functions can take any parameter. So it could be x equals to minus 9,999 and so on and so on. But let's just pretend this is an infinite range for a moment, just to provide some clarification. The global min would be the lowest point on the whole function. So as we can see here, this is the lowest point throughout the entire function. So we would classify that as the global min. And the global max here is the highest point throughout the entire function. And this point here is. So this is the global max. But today we're just going to talk about finding local min and local max. So how do we do this? I'm going to provide a step-by-step here, but then we're going to go into an example to provide solid understanding. So we find the first derivative and set that equal to 0. And then the next thing is rearranging that to find the values of x where the derivative is equal to 0. And those values here, this is an important concept, are known as the critical point. So when f dash of x uh, is equal to 0, the x values which make the derivative equal to 0 are known as the critical point. So we have these values. How do we determine if this critical point is the local min or the local max? So there's two steps. The first one is called the first derivative test. So we find the first derivative as we did here, and we sub in points to the left and to the right of each critical point. Usually it would be you could do -1 and +1, but as we'll see in our example today, we're going to use a range of -0.5 and plus 0.5 just to keep within the range. But if it fits in the range, it's usually smart to do -1 and +1. So if the derivative, so if you sum in, let's say here, if f dash of x minus 1 is greater than 0, and also f dash of x plus 1, so either side of the critical point where x is the critical point is less than 0. So the first one, I might highlight that a bit more, greater than 0. Um, this is the situation here. So, yep, so this is the situation here where the critical point -1, so f dash of x -1 is greater than 0, and the critical point +1 is less than 0, then that critical point, that x value, is the local max. And why do we say greater than and less than 0? Because at the critical point at x, it's always equal to 0, because that's how we found it. So if the left-hand side of that critical point, CP -1, is greater than 0, then it's a local, and also the right-hand side, CP plus 1 is less than 0, it's a local max. Conversely, if the left-hand side of that critical point is less than 0, and the right-hand side of that critical point is greater than 0, then that critical point is a local min. To double check that we've made the right judgment, we find the double derivative. So this is called the second derivative test. So we find f double dash, so that's just getting this function and differentiating it one more time. And we sub in the critical point. So we sub in the value of x is equal to 0 for f dash of x. If that critical point is less than 0, in the double derivative, then it's a local max, symbolizing concave down. If that critical point is greater than 0, then it's a local min, symbolizing concave up. And what do we mean by concave up? As we can see in this example, the CP here is the local min because look, it's going like a smiley face sort of. The CP is the lowest point, and concave up means it's like a smiley face. Here would be the local max, and concave down, it's like a frown. You see that? And then the final step is simply just subbing in that critical point value we found into the original function, f of x. So once again, I might just make that a little bit more clear. So we would sub f of CP, the critical point, into the original function, and that would be the corresponding y point. All right, so you might be a bit lost maybe, but I feel like through the next example, we'll get a clear depiction. So this example here, we have the function f of x equals x to the power of 4 minus 4x squared plus 1. And the question's asking us to find the local max and min within the range of x is a minus 2 to 2. I went ahead and did it on Desmos. So this is the graph it's produced. So let's flip from minus 2 to 2. Immediately we can see that this point here and this point here will be the local mins, and this point here will be the local max. We have two local mins, which is interesting because they're the exact same value as one another. These, as you can see, will produce the exact same set of coordinates. So there's two, but if one was to be slightly different, one was slightly lower, then there would only be one. And we have one local max, as can be seen here. But let's go through it mathematically. Let's pretend we didn't have this graph and we wanted to find this, this, and this. What would we do? So first, let's find the first derivative. If you do not know how to find this, I recommend looking at my introduction to differentiation video, which can show you. So we bring the 4 down minus 1, so we get 4x cubed minus 8x, remembering anything without a parameter goes to 0. We set this equal to 0, and we can just take out a common factor of 4x. So we already have our first critical point here. So we have 4x equals 0, so that means x would be equal to 0. And then we can just take the other one where x squared minus 2 is equal to 0. So bringing the 2 to the other side and taking the square root, we get x equals plus minus 2. Therefore, we have three critical points. We have x is equal to negative 2, x is equal to 0, and x is equal, negative square root 2, sorry. X is equal to 0, and x is equal square root 2. So let's perform the first derivative test. As you can see here, I've chosen points plus zero point 0.5 and minus zero point 0.5 because the square root of 2 and negative 2 is actually minus 1.41412 and 1.412. So if I did plus 1 and minus 1, it would be outside of that range from minus 2 to 2, but keeping it within the plus zero point 0.5 keeps it in that range. So f dash of minus 2 minus zero point 0.5, we just sub that into the first derivative, as we can be seen here, and it provides a negative value. The number doesn't matter so much, but the value matters if it's negative or positive. And then we do for the left hand. So we've done here now. Now let's find the on the right hand side the larger value of the critical point. So minus to plus zero point 0.05 now. Sub that into the first derivative again, we get a positive. And what did we say before? If our CP minus 1 produces the point on the left-hand side of our critical point produces less than 0, and the point on the right-hand side of the critical point produces greater than 0, then it's a local min. So we can already say here, minus 2 is a local min, which sort of confirms our understanding here. Now let's test for x equals to 0. For x equals 0, I could do plus minus 1, but just to keep continuity with the plus minus zero point 0.5 for square root 2, I will just do the same range here. It doesn't really matter, but it usually just tends to be easier with plus minus 1. So simply we sub in f of 0 minus 0 0.5 into the first derivative, and we get 3.5. And then we do f of 0 plus 0 0.5 this time, so the right-hand side of the 0 critical point, and we get minus 3.5. Once again, we go back here. If the left-hand side of the critical point, the lower value produced is greater than 0, and the right-hand side of the critical point, the greater value, is less than 0, then that CP, so 0 in this case, is our local maximum. Awesome. So we can determine minus 2 is a local min, 0 is a local max, and then once again, similarly for x is equal to 2, we do 2 to minus zero point 0.5, get a negative value, 2 plus 0.05, just to keep within that range of minus 2 to 2, and we get a positive value, confirming that x equal x for plus and minus square root 2 are both local mins because they go from negative to positive, and x equals 0 is a local max because it goes from positive to negative. Now let's just do the second derivative test to confirm. So taking the second derivative of f dash of x, we get 12x squared minus 8. So we just go to this one here and find the derivative again, just pretend it's a normal function. And then subbing our critical points in, we see the square root 2 and negative square root 2 are both equal to 16, and the 0 is equal to negative 8. Going back to our local min or local max, we see if the second derivative of the critical point is less than 0, it's a local max, concave down. And if the second derivative is greater than 0, then it's a local min. So once again, this confirms that x equals plus minus square root 2 are both local mins, as the second derivative is greater than 0, and confirms that x equals 0 is a local max, as the second derivative is less than 0. So now just to find the corresponding y values, we just sub them into the original function, as I said. So we'll sub the critical points into this function here. We have f of minus square root 2, sub that into the x to the power of 4 minus 4x squared plus 1, and we get a value of negative 3. F of 0, we get a value of 1, and f of square root 2, we get a value of negative 3. So therefore we can see both of these are local mins because they both have the same y value of negative 3. Let's say in a different world, this was negative 3.1, then we'll only have this one as our local min, as the y value would be lower. But since the y values are both the lowest points within that range, we have two local mins, and we only have, and one is the highest y value within that range, so we have one local max. Awesome. So that concludes today's video. I hope it's provided some understanding of local min and local max, and best of luck in your studies.